So it's 8:30 now, so let's get started. I hope you will enjoy today's conference. Okay, so good morning, everyone. So let's get started. Our first speaker of today is Peng Shan from Tsinghua University. She will speak about representations of simple affine vertex algebras at elliptic levels and affine sprinkler fibers. So let us welcome our speaker.
Thank you. I'd like to thank the organizers for the invitation. So what I'm going to talk about today is based on two joint work. The first with Dan Xie and Wenbin Yan. And then the other one is joint in progress. Wenbin Yan and Qixian Zhao. So let's start with a semi-simple complex Lie algebra G. And I'll fix a Borel and a carton. So let G hat be the affine Lie algebra associated with G. So it's a central extension of this loop Lie algebra. And then have the affine part of the carton. So okay. And then so for any complex number kappa, can consider the universal affine vertex algebra. So by V kappa G. There's a vector space. This is the induced module from U of G Z entity, and then you just let the central element x by kappa and the other use x trivially. So it carries a structure of vertex algebra. So this is universal affine vertex algebra. And it has a simple quotient, which I denote by, this is the L kappa. So let me write L kappa G. This is a simple affine vertex algebra in the title. So quotient. And as a vector space, it's just the simple representation, which appears as quotient. This representation. And so it's well known that the representation of the universal affine vertex algebra is equivalent to the category of smooth representation at level kappa. And since this is a quotient, so representation of this simple quotient, you can think about it as those modules here which are annihilated by the and so so it forms a subcategory inside here. And in general, we'll be interested in the category O, which is a category of highest weight representations. And then you can consider the corresponding subcategory, which consisting of modules over this simple quotient. Okay. And it's this category we will be interested in. So the kind of thing you want to understand is, for example, so what are irreducible objects in this category. And then for vertex algebra, there's a notion of associated varieties. How do I spell that? For L kappa of G. So maybe I first explain the result in the cases which is kind of now well understood, which is called the admissible case when kappa is at admissible level, and mention some relationship to affine Springer fibers, and then I will explain some background from physics for why we're interested in this kind of problems, and then I will go to elliptic level. So what we call admissible level, this is when kappa has the following forms. So kappa plus the dual Coxeter number is a rational number of the form p over u, where p is a positive integer bigger or equal to the dual Coxeter number, and u and p are coprime. And u should also be coprime to the dual lacing number. And in this case, so this how to say? So representation of affine the edge at admissible level was first studied by Katz and Wakimoto. As an extension of the study on integrable representations for affine the edge, because this is a setting where the characters also satisfies modularity. And in particular, a weight is called admissible if so yeah, lambda is an element in H hat U. It's admissible if first of all, lambda plus rho hat is dominant regular. That means if you pair it with any co-root, with affine co-root, affine real co-root, it doesn't belongs to the set of negative integers, including 0. And then secondly, you ask that there is an isomorphism of the vector space H check dual to itself, which sends the set of H, which H, no, this is B. This is rho hat. So which sends the set of co-roots integral with respect to lambda to bijectively to the initial co-root system for the affine lineage. Okay. So these are the elements in yeah, I put hat for my affine data. So such that alpha and lambda belongs to them. Okay. So this is the kind of weight which is not integral, but it's so this is the set of weights which sort of behave as integral weight, and then it's a result of it's a result of Arakawa that in this case, the irreducible representations of L kappa is actually what is so-called admissible representations for the affine Lie algebra. So this is the set of simple representations with highest weight lambda, and lambda is admissible of level kappa. So I will note the set of such weights by admin kappa. And moreover, in this case, actually, this category C kappa is semi-simple. So it really behaves as integrable representations. Okay. And then a situation which we were like interested in is in the so-called boundary admissible level. Choose algebra for L kappa. Yes. Yeah, we know the associate right is calculated by Arakawa, but I'm not sure if it's exactly by that. Ask me that question. So boundary admissible means kappa plus h check is h check over u. So this is when p attains its minimal possible integer. And so in particular, at boundary admissible, there is only one variable, which is this u, and which is required to be co-prime to h check. And also to r. And in this case, the set of admissible weight has a very nice description. It is simply you let the elements in the affine Weil group dot acting on kappa of lambda 0, where lambda 0 is the 0th fundamental weight, and then you impose the condition. It sends a certain set of affine weights to affine co-root to positive co-roots. So here, u check is the is like u times I do one as the dual of this lambda 0, and then minus theta check, where theta check is the shortest highest root, highest co-root, and then alpha I check, and these are the simple co-roots, simple finite co-roots. So I just write one I bigger than 1, smaller than I. Okay. So so for when your level is rational, it's not hard to your kappa lambda 0 satisfy this condition because you're just dilating the direction on the center, and then so therefore all these elements satisfy the second condition because you're just up to shift by row, you're just doing a linear transformation, and then this condition makes sure that your weight obtained like this is dominant, right? It makes sure it's dominant. It's automatically. So this is a description of the set of waves. And now from there we want to make a link to affine Springer fibers. So I'll just write ASF for affine. It's just so it's the carton is the finite carton plus c times the central element. Yeah. Okay. And here I take G check Langlands dual group. And assume it's simply connected. Well, may not be exactly what I. Maybe let me just simplify it. Let me say I take so the description I'm going to give you. How should I put it? Maybe I should put it like this. So I should take the associated with the, let's say, the Katzmuni group of, let's say, simply laced type, simply connected Katzmuni group, and which is of type due to the is the Langlands of the affine algebra. Okay, so in particular, when G is not simply laced, this is a twisted affine algebra. But to just simplify this talk, let me write things more concretely in the case of simply laced type. So so let's say G simply laced. And then let K be the field of Laurent series, and then O the ring of integers in K, and then we have the loop group associated with this is just the Langlands usual ones, GK, GO, and then here you have an evaluation map to G check just by evaluating Z equals to 0. And then the pre-image of Borel under this map is the Iwahari subgroup. And then as I said, this affine flag variety is just quotient by I check. Okay. So for any element in the affine Lie algebra, I can consider the so-called affine Springer fiber. And as I said, this is a let's say this is an subscheme inside the affine flag variety, and then consisting of the elements such that if you do joint action of G minus 1 on gamma, you still get an element in the Lie algebra. So this is the definition for affine Springer fiber. And in our situation, we'll be considering a very particular element where I'll take gamma just to be the sum of, so each of my co-root here will become a root for the dual affine Lie algebra, and I just take a root vector in for each of them. So I take E alpha I check. And then for U for U1 minus theta check, this corresponds to F theta check Z to the power of U. So let me denote this element by gamma U, as I'll probably explain the terminologies a bit later, but this is a so-called this is a homogeneous elliptic. It's U, yes, U. Elliptic regular element. Third type. And for this gamma, this affine Springer fiber in general, it's an in scheme and can have like infinite many irreducible components. But for this particular gamma, it is a nice finite dimensional projective variety. So it's a projection. And it carries a C star reaction, which is defined as follows. So you first consider a co-character for the following torus. So you take T check to be the maximal torus in G check, and then it acts on the affine flag variety by left multiplication. And on the other hand side, you have you can dilate your Z variable, get the loop rotation action. And so all this big torus acts on the affine flag variety, but it does not preserve this affine Springer fiber. There's no reason that this property being preserved. But you can look at a subtorus star, which is given by sending an element to. So here you take the co-character defined by rho. So rho on, so U times rho, where rho, like my notation is always precise. So this is a co-character for T check. And then T to the H check. And then you can, by an explicit computation, you check that when you take elements in the subtorus, the action on gamma U, it will just dilate the element. And therefore, the C star reaction preserves this affine affine Springer fiber. So you have this gives you a C star action on this gamma U. And the fixed point is actually just because U is regular. So the fixed points is just you take the usual T check fixed points in the affine flag variety and count and take those which belongs to this fiber. And this set is canonically identified with the affine Weyl group. And it's saying that it belongs to this set just says that you take the element which sends these roots to positive. So this is the same as the set over there. So this is let's say X belong well, yeah, X belongs to a affine well group such that, except I have an X inverse. So X inverse of pi U belongs to phi. Okay. And so no, I think their motivation with the characters of these representations has modularity. It has modularity. It has SO2Z action on the yeah. Yes. Yes. No, in fact, the non-boundary case is not so difficult to recover from boundary case. You have some other components. It's, I think they have it for all the admissible cases. Yes. So we are restricted to boundary cases because like if you're not boundary, then somehow, how do we say this? So boundary case is like something inside the category O, inside the block of a category O. What I said doesn't make sense really, but the idea is like if you want to have non-boundary situation, you need to take several copy of Springer fibers. Yeah, no, I'm not going to say anything about admissible non-boundary, but I'm going to say something about non-admissible. That is more, yeah. Okay, and so then here basically follows from what I just explained. Then you notice that so let's say the first result. It's not a complicated result, but I'll explain a bit later why I'm interested in this. So that as you notice, there's a natural map from the C star fixed point in the affine flag variety to the set of admissible weights just by sending an element to X inverse dot kappa lambda 0. This is a bijection. So let me say this is the first part. And then the second part, we can also say something about the modularity property. I think I will not go into so much details, but just explain the idea. So so as we just discussed, what was shown by Katz and Wakimoto is that if you take the space of characters, or maybe let's say you take the span of the characters of these admissible representation, and then Katz and Wakimoto showed it carries an SL2Z action. On the other hand side, you can take the Grothendieck group of this, let's say, coherent sheaves on this fixed point variety, and according to some geometric theory, this is a module over. This is a finite dimensional module over double affine Hector algebra. And by work of Ivan Berenik. So it also carries a nice SO2Z action. So it's actually a so-called perfect module. And so the bijection here, up to some modifications by signs, which I'm not being precise enough to tell you that, but you use this to establish a bijection, an isomorphism between the two vector spaces, and it's actually compatible with these two SL2Z actions. So so it's an isomorphism as SL2. Yes, yes. No, I don't. Yeah, I hope so, but for now, it just function on the points. Yes, yes. Okay. So, but somehow, yeah. So, but somehow it was from this point of view that we thought about comparing this SL to Z. No, this is no this SL2Z action comes from data theory. Well, you can also you can describe it. You can write it as explicitly, but it comes from so the ST metrics have some very nice meanings in data. The idea is you have some automorphism of Daha, which is a central extension of some of SL2Z, and then and you have an action on the module which intertwines that action. Okay, and then maybe a final part of this theorem is that so this bijection. So the story we're telling here is compatible with reductions to W algebra. So maybe I'll just say, so on representation side, you can do Drinfeld Sokolov reduction. To be more precise, there are two versions of them. You need to take an exact one. So it's a minus version of Drinfeld Sokolov reduction from L kappa to W algebra. So let's say a W kappa of G associated with the nilpotent element. I need to assume F is regular in the middle. And this is compatible with reduction from affine Springer fiber to affine Spitz-Stein varieties. If I write in that, so it's a subvariety in some G in, let's say G, a parahoric subgroup such that this F is regular in the naming of this parahoric subgroup, and so this, let's say inside here you take those elements G of such that the joint action of G inverse on gamma U belongs to the Lie algebra of the radical of P-check. So what happens here is that when you do the Drinfeld Sokolov reduction, then simple modules goes either die or go to a simple module. And it may happen also like two simple modules go to the same one. And when you compare like this variety to this, the radical of P-check is smaller. So some of your points here will not belong to here. That corresponds to the module who will die. And then those which do belong to here, but here you're taking a quotient by p check. So like this is a quotient of the affine flag variety. So your points can coincide in this quotient, and that corresponds to the simple modules which coincide after the reduction. So these two procedures are really compatible in this picture. And you can also descend the SL2Z action, the modular group action is also compatible. Okay. Okay, so maybe let me say a word about how we started and why we were interested in this. Yeah. There were no yes because yeah okay, sorry, yeah, I'll explain more. So your t is something like q to the power of kappa or the other way around. So this, yes, and then you need to specialize at the end t is equal to 1 and q is a root. Yeah, so I mean this is right. So yes, so this is only a very specialization, but I think there are some yeah, but maybe we can discuss about this later. There might be some way to, I mean, I don't think for now we have any understanding of a generic version. Like there's no way to make Q generic for the moment, but you can interpolate, like it's possible to make Q other roots of unities. Okay, and so our starting point was from the so-called 4D 2D duality in physics. And so for any 4D n equals to 2 superconformal field theory, there's a 4D 2D duality functor which associate a vertex algebra to any of the, to each theory you get a vertex algebra under this functor. And then so if you specialize to so-called class S or generalizations of class S theory, then there's a conjecture which is proved in some special cases by Arakawa is that the Higgs branch is given by the associative variety of this vertex algebra. So let me just denote it by X of VT. And then the Coulomb branch in this case is given by some Qixian moduli spaces. So a class S theory is attached with the Riemann surface. So associated with Riemann surface. See, and then the Coulomb branch is given by the Qixian moduli space. of Higgs bundles on C. And for what we are interested in is so-called generalized algebras theory. Where this admissible L kappa shows up. So this is quite so like in part of this theory there exists some T kappa here where when you go to this functor gives supposed to give you L kappa, and then there's a better understanding. Like here, it can be more precise. This is a moduli space of Higgs bundles on P1 with a regular singularity at let's say at 0 and an irregular singularity at infinity. So the order of the irregular singularity has to do with this kappa here. And then for the regular singularity, you can also attach a nilpotent class. So this can be L kappa or W algebras associated with L kappa. And then so in some particular cases, there have been, like in physics literature, it has been noticed that there's relationship between C star fixed point on the Qixian moduli space and irreducible representations for L kappa. And our motivation, like for that thing, is to just write it for general case. And the relation is this is similar to what Roman explained yesterday. The fine Springer fiber we're considering actually sits here as a Lagrangian central fiber. So so that's the relationship. And now you can, with this picture in mind, you can ask more questions. So the fiber we consider is really a very particular type of a fine Springer fiber. So the gamma U I wrote for you, so it's an invisible case. This is so-called an elliptic element of Coxeter type. So it's elliptic of Coxeter type. But you can ask what happens for other homogeneous elliptic fiber. So I will explain a little bit later. You can associate I mean, it depends on an elliptic regular number, and you can consider the vertex algebra at the corresponding level. And you might want to know, does this picture generalize to those situations? And then no, I'm not doing any two-parameter story. Yes, I'm going to do U equals to 1, but I'm going to change the H check. So yeah. So yeah, okay. And also there is another question, like suppose now you have you have this picture, you have your fine Springer fiber, and would it be possible to read your Higgs branch from the Coulomb branch? Like, is it possible to understand, to describe this associative variety from this Coulomb branch? So that is another question? Is it possible to read? Let's see. Sorry. And finally, there's a prediction from physicists that all the Higgs branch should have only finitely many symplectic leaves. So and this, by definition, means this vertex algebra is so-called quasi-leaves. But it's clear that, well, there are examples which shows that this L kappa is not always quasi-leaves. So, so that means that they cannot all appear, like, well, in some sense, they cannot all appear in this theory. And so, like, you can ask, like, for which kappa L kappa is quasi-leaves. Okay. So this is some of the questions like to discuss. So so I want to first say a word about elliptic elements. So in general, in the theory of affine spindle fibers, we always like for the fiber to behave nice, you consider so-called topologically nilpotent and regular semi-simple element. I will not describe what topological nilpotent means, but regular semi-simple just means its centralizer is a Cartan subalgebra. And then the Cartan subalgebra in the loop group, or the max, let's say in three check hat, modulo conjugation by G tech K. This is in bijection with the conjugacy classes in the vowel group. So, so we say that gamma regular semi-simple is of type a certain conjugacy class W in. So this is conjugacy class in the finite vowel group. If its centralizer is of this, it corresponds to this. If centralizer of gamma is of type W. Okay. No, for now is general. And then I will consider a homogeneous element. So gamma is homogeneous if if it is conjugate, let's say homogeneous of slope nu, which is a rational number. If it is conjugate in G, where you take the algebra closure of K to an element of the form T, let's say an element in the finite Cartan times T to the power of nu. Okay. And now if nu is let's say a rational number of type U over M, where let's assume U and M are co-prime to each other, and let's say they're both positive. Maybe I'll just say M is positive. And in this case, there exists a homogeneous regular semi-simple element of slope nu, if and only if M is a regular number for W. So it is the order of a regular conjugacy class. And then, yeah, and then there's a notion of elliptic element, which basically means it doesn't have non-trivial co-characters. So gamma is homogeneous elliptic regular semi-simple. If and only if M is a elliptic regular number. Okay. So the Coxeter number is a particular elliptic regular number, and then there are other elliptic regular. Well, in type A, this is all, but in other types, there are more elliptic regular numbers, and so you have more fibers. Yes, exactly. And when gamma is elliptic regular semi-simple, Peng Shan proved that the fiber are always finite dimensional. Non-perfect harmonious, exactly. Okay, and so now to connect the Coulomb branch and the Higgs branch, what we consider is the following. So Lustig defined the map from conjugacy classes of Well group to conjugacy classes to like orbits in the nilpotent cone. I'm taking the nilpotent cone in a dual algebra. And then okay, Yun give a different description, but I think for time reasons, maybe I think we really use his description, but for time reasons, I will maybe not describe it for you. Okay, so what is the proposal? Maybe let me get to the conjecture directly. So we would like to propose the following conjecture. This is with Wenbin and Qixian Zhao. That so we take M, we assume kappa plus h tag equals M is an elliptic regular number. So notice like before I took h check over u, and now I'm taking the case u equals to 1, and then but I allow this to be smaller than h check, and then we assume that phi of so you have so this there's an elliptic conjugacy class this order, so corresponding elliptic conjugacy class. And you can take its image under phi, and you assume this is distinguished of it. Then the conjecture is that the associative variety of L kappa is given by the dual of it, so phi of Wn, where D is this this Barber-Schrogen expectation is a composition of. So yeah, so it's a dual of this map, and then I take the closure. So in particular, this implies that, well, if this conjecture is true, this implies that in these cases, this L kappa is quasi-Lie, because this lives inside the nilpotent cone and has only finite leaves. So there are some known cases for this. Well, the problem is that there's not so many things understood on the vertex algebra set, but these like non-admissible levels have been studied by some people, and in the cases where it is studied, it is compatible with this conjecture. So maybe.
Some kind of age of this particular
No. It's okay. Maybe let me just say so. This distinguished condition is really for like m/1 cases, and we expect this to hold in some more general situations when there are rational levels. And for example, so first of all, if you take, let me say, admissible case, this statement is true. So let me put star. So star is true. The idea is most of the cases this orbit has been calculated, and you can look at this dual. And in admittance, our computed the associative variety, and it really matches this. And then one case which is interesting is so-called the subcoxeter case. For the subcoxeter case, this on the vertex algebra, this corresponds to so-called Deligne exceptional theory. And so if we look at only like simply laced type, then the corresponding roads. Okay. Sorry for girls. So these are the elliptic. It's all recorded, and so in this case, the orbit is this phi of Wm. This is the regular orbit, the subregular orbit. And then so if you take the dual, it's the minimal orbit on the other side, and it has been proved by Moreau and Arakawa that in the corresponding level, the associative variety is the closure of the minimal orbit. So this is a case which is okay. Simplest, yes. I think. Yes. No, I mean, I guess we also computed some cases for non-simply laced situation, but you need to do twisted stuff. Okay, and then another family of example is in type D. So if you consider level 3 minus n of type Dn, where n need to be even, and in this case, actually n equals to n, and then this is the elliptic level, and in this case, it also holds. Maybe I don't write the answer, but this case works. So yeah, like maybe I just say one word to finish. So what I want to say, so this is about the associative variety, and then we also expect to have a correspondence of modules. So for these cases, you can take so you fix an m, which is elliptic regular number, and then you take gamma is a elliptic homogeneous elliptic regular semi-simple element of type Wn. Then you still have a C star action on the corresponding affine Springer fiber. But in these cases, the fixed points are, well, the fixed point locus are no more isolated points. So it can have higher dimensional components. So it's a union of certain, let's say, Heisenberg varieties with some explicit parametrization set. And then but again, we conjecture that so with the same assumption, so assume phi of Wm is distinguished, then if this Heisenberg variety is not empty, then L of W inverse dot kappa lambda 0 should be a module for this simple affine vertex algebra L kappa. So I just give you a picture of what's happening in this D4 situation. So for this, so this is a subvoxelar case, and D4 and D4, and in this case, the fiber is 5p1. And then if you take the fixed point component, so you still have the p1 in the middle, and then you have 4 points. And if you apply this formula, it will precisely give you the 5 irreducible modules for L kappa in this case. Okay, I guess I'm done. Thank you.
So it's time for questions. So in your question two, you said how to read this associative variety from this Coulomb branch. So in all these cases, what's the relation between these varieties and the corresponding Coulomb branches? In those cases of this X.
So the idea is the basic idea is that you have some you define some Weyl system such that this Springer fiber is the Lagrangian fiber for that Qixian system, and that's the Coulomb branch.
Yes. Then what's the relation between the Coulomb branch and this Newton orbits?
The Higgs branch is the associative variety. So this is telling you. So here I'm like starting from the Springer fiber, and then saying that the associative variety for the vertex algebra, which is conjectured to be the Higgs branch, is given by this procedure. Does that under you? No. No, I don't give any general construction like you starting from a Coulomb branch how to produce your Higgs branch. I'm just saying, in this situation, I mean this tells you this gives you a conjectural answer for the how the Higgs branch should look like. Is this yes. It's it's associative right.
Okay, so we have one more questions. Okay, so let's thank our speaker again.